Afternoon. Welcome to the Scripps Technical Forum. My name is Douglas Alden. I'm the lead engineer for the Center for Western Weather and Water Extremes, and I'm also the chair of the Scripps Technical Forum, and I get help from Gwen Nero and Vanessa Scott in organizing and get speakers for these events. Today we're going to, as always, you're muted when you're on here, and we're going to have a Q&A at the end, and you can raise your hand to be unmuted. And then you can ask your question, or you can use the Q&A function down in the Zoom to put your questions there. We also did receive some questions prior to the presentation, so we'll make sure to cover those as the talk goes on. And with that, I'm going to hand it over to Chad Collett from the presentation today. Thank you.
Hello, my name is Chad Collett, founder and CEO of SubC Imaging. I'm honored to be presenting today as part of the Scripps Technical Forum, and a big thank you to everyone that has joined us today. In this webinar, I will be using the development of the tow camera system, SubC's newest innovation, as a case study on how regular collaboration with customers can drive innovation in coastal mapping technology. I will also discuss the why behind the tow camera system and how understanding the challenges of marine surveys and seafloor mapping inform our product design. We'll cover the innovations developed through collaboration with scientists, approaches in new field testing, improving the tow camera system, and the benefits of the tow camera system beyond fisheries research. At SubC Imaging, we develop and deliver imaging systems and software solutions that meet the unique challenges of marine science, fisheries research, and offshore energy. When I founded SubC almost 12 years ago, we had one product and a handful of clients. Today, we have more than a dozen products and systems, from standalone cameras that take crisp, clear images in depths up to 6,000 meters to complete observatory systems, and even secure video streaming software for marine surveys and remote autonomous operations. We're a small team with 25 members, but we serve more than 180 clients in over 30 countries. First, let's discuss the why behind the tow camera system and how understanding the challenges of marine surveys and seafloor mapping informed our product design. We are constantly looking for ways to refine and upgrade our camera systems and our products so we can remain on the leading edge of subsea imaging technology. Part of the reason for our growth and how we've stayed at the forefront of underwater imaging is that we are constantly and continually collaborating with our customers. We're always thinking of them and the problems they face when developing a solution. Many of our customers operate their own tow camera systems, often developed in-house, and no two camera systems are the same. System development is difficult, and our customers' end goal is to conduct scientific research. But what we've found is that scientists are often having to develop technology just to enable their research. So when we identified a potential need in market for a complete off-the-shelf seafloor mapping and imaging solution, we knew we needed to learn more to validate our thinking. The first thing we did was have meetings with Marine Institute's group, the Center for Sustainable Aquatic Resources, and their researchers who do seabed towed camera science. We wanted their feedback and to understand the challenges they face when mapping and imaging the seafloor. We also pulled in the Government of Canada's Department of Fisheries and Oceans, who we came to discover face very similar challenges. This same feedback we came to learn is shared by other subsea customers and companies in the marine observations, fishery research, and conservation fields. There are four main challenges in seafloor imaging and mapping: the gaps in seafloor mapping solutions, the time-consuming and costly DIY, the environmental impact, and the need to be future-proof. Problem number one, the gap in seafloor mapping solutions. So there are no off-the-shelf and easy-to-operate systems that cover all of the areas of coastal and offshore seafloor mapping. When an ocean survey needs to cover a wide area in high-resolution digital stills or video, there are only a couple of options: either get an expensive AUV or develop an in-house custom-made drop camera system. Time-consuming and costly DIY, number two problem. In order to collect the same type of footage and post-survey report generation, clients currently have to build their own system from a collection of components, which can be time-consuming and costly. What's more, the success of these homegrown subsea imaging amalgamations relies on constant trial and error and troubleshooting. In my time delivering products and solutions to customers for their drop and tow camera systems, I've noticed that no two of them are the same. This can be okay, but it also means that each research group has to have dedicated personnel for development and maintenance of these custom systems. Our goal is to free up budgets and skilled personnel so that they can conduct more science. Here are just a couple examples of customer-built systems. Often, drop or tow camera systems are built to be heavy, so they can hang vertically under a vessel. This often means that in addition to signal cables, they also need a heavy lift wire. This requires 2 sets of cable management sometimes, and additional complexity that comes with that. Or, the drop camera systems are running on batteries autonomously, so there's no live feed to the surface to guide operation of the system. They're also often designed to skid or have some form of bottom contact, at least on an intermittent basis, and they usually look like slides or toboggans because of this. This can be okay as well, and is often about the type of science you intend to complete. But we've noticed many common goals and trends over the years across multiple systems with many customers. This is an example of video captured with a tow camera sled where there's no live feed to the surface. The operator has to rely on intuition and experience to determine if the system is working correctly. It touches the bottom, so there's a need to adjust based on incoming seafloor features on the sounder on the boat or on the GPS. It can get hooked up in obstacles and operate as an anchor as well, but the operator will not know until the cable gets tight. Experience can be built up over time to get good at operating such a system, but this experience is learned, not trained, and can be costly to develop. And problem number 3, environmental impact. Some surveys need to traverse through marine protected areas or are unable to assess certain habitats. Researchers are conscious of this and want to avoid potentially damaging environmental impacts. However, this also prevents them from fully gathering all the data they need to make good decisions. So it was important for us to design a system with this challenge in mind. And problem number 4, the need to be future-proof. So like any business organization, priorities are always evolving. Because of this, the Marine Institute and Department of Fisheries and Oceans wanted a system that would work for their current initiatives, but also help in future applications. The system also needed to be cost-conscious as budgets evolve while still providing the ability to produce high-quality images they need for their initiatives. With the challenges identified, the SubC team went straight to work. We already had the top quality solution to take 4K and HD video and stills with a ray-fin camera and our high-performing LEDs and lasers. So our main focus was on designing a cost-effective frame and tow solution. Now that we understood the problem, we were able to move to developing the systems themselves. We started with research into what our friends in the scientific community have been using, as well as interviewing our customers who operate drop and tow camera systems. Through our research, we decided to base our design upon a few proven methods that are detailed in scientific research papers. An example of one of these research papers is CSIRO's in Australia. They published a very detailed paper. It's called a vessel-towed camera platform for surveying seafloor habitats off the continental shelf. We learned a lot from this paper. We kind of based our initial design around it. You can see that it's a circular frame. It's quite large. It's a couple meters across and more than a meter in diameter. But it's called tacos. It had a drag chain, as you can see there in the black and white photo. And it had some flotation, but it was very large and it was a collection of components. Another paper we studied was the University of Plymouth, Griffith University, and some other universities in Europe. They had a joint paper published as a side-by-side accounting of various methods of seafloor mapping. It's called a quantitative non-destructive methodology for habitat characterization and benthic monitoring at offshore renewable energy developments. This paper had side-by-side comparison between tow systems that have some bottom contact, tow systems that have flotation, tow systems that have a drag chain or anchor, and they highlighted the pros and cons of each. And it really saved us some time in testing. We didn't have to redo the same science that they did. So we took the concepts outlined in a number of scientific research and our own experiences with working with customers, as well as feedback, and we miniaturized it. We made it our mission to reduce the costs and increase the ease of use. From there, the team was able to design a prototype that had the following: a stable, rugged frame, an all-in-one system, camera and everything. We also developed new subsea boost power communication technology to solve some critical things around cabling, and an environmentally conscious design as well. The frame is built to be hydrodynamic and stable while maintaining a constant altitude. The rugged design allows the system to maneuver over obstacles like rocks or fishing traps, and this makes it the ideal solution for collecting transects of seafloor footage from vessels working in coastal water. The result, as you'll see, is a very smooth video and images from a consistent altitude. Instead of research groups having to develop their own tow camera platform and integrate various sensors and software, they can obtain a ready-to-deploy system complete with frame, tow cable, camera, control software, lights, lights and LEDs, same thing, lights, lasers, and data logger. We've even partnered with another Canadian company to provide an optional winch system to complete the full package. One of the biggest innovations that happened during product development was SubC's new boost power communication technology. This technology can transmit power and data over a long length, low cost, twisted pair subsea cable. It can provide enough power to drive the camera, 2 LEDs, lasers, and other sensors, while also enabling live HD video and data to the surface. The cable is a Kevlar embedded tow cable that has just 2 conductors in it, so the cost is reduced dramatically. We know how important environmental stewardship is, so the system has been designed to have very little contact with the seafloor. This is achieved without any active components such as thrusters, so the intelligent design uses hydrodynamics, buoyancy, and a small drag chain and clump weight with embedded altimeter to passively collect and control distance to the seafloor from the camera system. This ensures that photos and video have a consistent subject distance. The system mechanics are unconventional, as you can see in the clip, but the end result is a very stable, low impact system. I'll explain how this works. The flight performance of the solution is based on its mechanical design and does not rely on active components. The vessel has a winch with an A-frame or side-mounted boom. Winch controls are ideally located at a PC, which is also running the camera software with live video and data. The full system during towing can be operated by one person, and in the event of a bottom snag, say with a ghost net or some other obstruction, the winch has a built-in slip clutch which pays out extra cable under high loads. The tow cable doubles as both a high-strength lift cable and also carrying power and data. It is rated to 455 kilograms or 1,000 pounds of tow strength and 1,500 kilograms or 3,300 pounds of braking strength. Strength comes from the Kevlar, which keeps the size of the cable to only 9 millimeters. The 30 kilogram clump weight has an embedded altimeter, which gives a real-time reading in the topside PC software. The distance to seafloor is directly controlled by the winch pay in and pay out, which is the only active mechanical part of the system operation. Camera has a field of view of 81 degrees. It can record in HD or 4K and take digital stills up to 3 Hz. Photos are also captured at with strobe synchronization, and the camera doubles as a data logger, recording depth, altitude, tilt, and roll, as well as GPS and other data sent from the surface. The drag chain and orange syntactic foam buoyancy provide passive altitude control and a minimum seafloor interaction. Nylon rope connection to the chain can simply be increased to raise the altitude, raise the subject distance off the seafloor. It was essential that we develop a system that would address the pain points our clients face when mapping the seafloor. So after we developed the prototype, we set out to rigorously assess the product's design. To ensure that we evaluated a product with a group that would be critical of the prototype's performance, we engaged two SubC customers, once again, the Department of Fisheries and Oceans and the Fisheries and Marine Institute, to give us honest feedback. The first iterations of the prototype were tested at the Marine Institute's Center for Sustainable Aquatic Resources in Newfoundland, Canada. This is the home of the world's largest flume tank. The tank can simulate underwater and near surface conditions up to 2 knots of water speed, making it the ideal place for early design assessment. In this clip, you can see the tow camera system and the velocity of water that has been designed to operate in and fully tested against. The ideal water speed for a system is about 1 knot. And in this clip, you can see a line laser for object scale and machine vision. You can also see that the camera strobing is strobing LEDs, and in this video it's at about 2 Hertz frequency, so 2 stills per second. After both flume tank tests, the prototype was modified and the system was ready to be ocean tested. First sea trial took place in the Atlantic Ocean in Holyrood Bay, Newfoundland, Canada, and together with the Marine Institute. With the results from our first sea trial and subsequent modifications, we have optimized the hydrodynamics, and this was key to moving from a prototype to a production version. Once the team was confident and we had a production version of the tow camera system ready, it too was tested in multiple other sea trials in Terranova Park in the Atlantic Ocean with the Department of Fisheries and Oceans. While the idea was born to help clients with marine benthic monitoring, the potential for a tow camera system is much broader. This is the research team on an expedition in northern Canada with Kikatelik Corporation and the experts from Marine Institute's Center for Sustainable Aquatic Resources. And this is footage that the Marine Institute has captured from a previous expedition. This footage was captured using all of the components from the tow camera system except for the new hydrodynamic frame design and clump weight. The video is captured at 150 to 250 meters of depth. This footage is captured with a bottom contacting tow sled. The operator has a live view of the scene because they're using SubC boost power communication tech, so they're able to control all the camera settings and see live data. Even though it's bottom contacting, this method of seafloor species data gathering is much less destructive than bottom trawling and sample recovery. You can count the number of species and individuals in an area, or estimations of biodiversity and biomass. This method is very repeatable and reliable for establishing baselines. The same transect can be sampled year over year. The camera angle is 35 degrees from horizontal. The methodology they use for this footage is to overlay a perspective grid. Our partners in the industry have established this method over the years and have made many discoveries and published multiple papers using this method. They are always open to new ideas and improvements to the way they collect data to inform science. We're incredibly thankful to the Fisheries and Marine Institute for helping us develop our new tow camera system. Fisheries and Oceans Canada operates a number of small and large vessels for their scientific research. Our goal was to design the system to be deployable from smaller vessels, and we achieved that. And here's an example of footage that was captured with the entire tow camera system, including the frame and the clump weight. The only difference between previous footage and this footage is that hydrodynamic tow camera frame with the passive altitude control. The camera is the same with subsea boost power communications tech, and the operator is able to view a live HD feed topside while seeing data and controlling camera settings. Both systems are using the same LEDs, the same lasers, and even the same Kevlar tow cable. Again, the only difference is the new tow camera system, which was developed with collaboration from our friends in the scientific community. You can see how this system glides over small obstacles such as rocks, and large obstacles such as hills and slopes. The lasers are in both videos as a visual reference for size and distance estimations. Mounts are adjustable from 21 degrees to 90 degrees from vertical in 7.5 degree increments. So you can angle the camera however is best for your survey. The system is adjustable from 1 meter to 3 meter height from seafloor, so you can account for visibility and how close you want to be to the subject. With these settings and with these adjustments, you can get very consistent, repeatable footage again and again over the same area or over a wide, long transects. The system can be towed at up to 1 knot and for many kilometers at a time. And it can store over 10 hours of 4K, 40 hours of HD, and thousands of digital stills. In the development of the tow camera system, we had discussions with other organizations to see how else the system could be used. We've had interest from those investigating archaeological sites to fisheries research and conservation projects. It can even be used for search and rescue, really any kind of ocean survey that requires consistent transect imaging of the seafloor. We've just launched the tow camera system officially into the market. We will continue collaborating with partners and customers to make improvements on this system. To keep the innovation moving, we look forward to hearing from our friends in science and industry. At this point, I'd love to answer any questions. Hi, Doug.
All right, Chad. So one of the questions that we had from the RSVP forum was, I'm interested in video quality and in particular how the tow camera maintains a consistent distance off the seafloor. I think you covered that in the presentation, but maybe you might want to go into some more detail.
Yeah, so the way it works is there's a drag chain that's weighing the system down, but at the same time there's flotation built into the frame that's pulling the system up. So those two opposite directions of force work together to keep the system at a consistent altitude, and you can set it at any distance from 1 meter to 3 meters off the bottom by adjusting a piece of rope in between the chain and the frame. And the clump weight that's pulled ahead of the system helps to maintain that consistency by removing the effects of ocean movement on the boat and other things that would affect a normally deployed drop camera system, where you would need some form of heave compensation. This has that passive heave compensation as well.
All right, next question is, how can it be applied to deep sea exploration? So
the question, I guess, comes around how deep. Currently, the system is designed and is based on cable length. The max deployable cable length right now is 410 meters, and that limits the system to 380 meters of sea depth. So sometimes I've heard deep sea being considered like, past 3,000 meters, but it comes down to the definition, I guess. This system has a max rating 380 meters right now. We are working on enabling up to 500, but we're not there yet. And that would just be in improvements in cable technology. We have other solutions for deeper, and yeah, so this one's 380.
Yeah, and I think a follow on to that popped up in the Q&A was Do you get one knot? I think you mentioned you can tow the camera at 1 knot, and that would be at the full depth that you mentioned.
Correct.
Okay, great. So how is the towed camera tracked? Does it have geo-positioning?
Yes. So, well, it's based, there's two methods. You can attach a USBL to it, and that would require you to have that USBL capability on your boat. And then you would get the GPS fix of the system as it's towed. A lower cost method that we've enabled is you can actually inject your vessel's GPS position into the camera in real time from the topside PC. And it's compatible with all NMEA format GPS signals. And the GPS position will be logged in a CSV file. It'll also be logged as in the EXIF data of each JPEG that's taken.
Great. What are the available data overlays and customization?
So there's no classic like data overlay per se. We log NMEA format data, but we don't put it all up on the screen. So right now, what you get on the screen is your tilt and roll, your altitude, and your depth, and you can inject any type of data in, any type of NMEA formatted data.
And that's saved separately in a data file, or
Yeah, it's saved separate. Precisely, yeah, Doug. It's saved in like a data file that has a timestamp, and the timestamp for the data file matches the timestamp for the video and the images.
Great. What are the limitations of the technology?
Limitations, tow speed. So you wouldn't be able to tow it at the full speed of the vessel. So that's limited by just the mechanics of it, how it works. You would end up, if you go too fast, you'll end up dragging the system behind the boat. And depth, I guess, which we covered. The 380 meter limit is the current limit right now. And that's really it. And I guess the topology you want to tow it through, you wouldn't tow any type of drop camera system through extremely mountainous terrain where you have giant cliffs. You should plan your dive your plan, look at your topographical or hydrographic map, and plan out a route in parallel with coast, not going towards the coast, because that would just make it more difficult to use.
And I guess you mentioned it in the presentation, but maybe you want to mention again how much video and still images you can record.
Yeah, so 10.5 hours of 4K, 40 or more hours of HD, and I think it's 20 to 40,000 digital stills. The amount of digital stills can be increased as well, and you can set the system to record or take stills at a constant frequency up to 2 or 3 hertz. So you can take 2 or 3 stills per second. So then you can get your overlap between your stills and start doing some more advanced things with it, such as orthomosaics and other interesting things that people are looking to do.
So, can this system be run on other pre-installed cables, such as armored coax? And if so, how does the altimeter clump weight connect in for the data stream?
That's an interesting question and difficult to answer directly, but we can definitely help with that. You would send an email off to us and say, hey, here's my cable that I have. Would this work as a plug and play type of thing? Or, or is there something you already have that could solve the problem I'm trying to or solve the solution I'm trying to achieve here?
So can this technology be efficiently used to do benthic biodiversity estimates, and can it work in low visibility?
Yes, it can be used for that application. And to the second part, it depends. Visibility and camera systems, it all depends on how close you are to the subject. So with the adjustability that we've added in for seafloor height, if you're in a really highly viscous area where there's a lot of sediment in the water column, then you would reduce your height to seafloor so that you're closer to the subject and you're limiting the backscatter from the lights, which we've position as optimally as we can to eliminate that backscatter. But there's no like measured viscosity limit. You know what I mean? Like it's hard to quantify. And if you're doing oceanographic work, you're familiar. Some days you go to an area and it may be fantastic, excellent visibility. And other days you may go back. It could be a weather event or a high rain or some kind of current change. And you, no matter what you would use, you wouldn't be able to see. So it really depends.
Is the tow sled system available for rent yet?
Not for rent yet, but that's an interesting question. And we do have partners in industry who own similar systems in our technology and are renting it. They don't currently own the frame, but that's definitely a possibility in the future.
And from the Q&A, we've got, is it difficult to add some extra payload, such as a microcat, to the tow body? And how difficult would it be to balance the tow body with the extra payload?
So we have added in the capability. It's like an add-on. There's a couple extra blocks of flotation that go in line with the main flotation. And there's actually balancing plates. We trim it at factory here, trim it out for the system as it is delivered. But we can actually, there's two ways it could go. We could get your extra payload. We could trim it out and install it and ship it out that way. Or we can send out extra plates and flotation depending on the weight of the system that you want to integrate.
And what would be the process if someone wanted to trim it out themselves, and did they do that in a tank before they went to sea? Is probably the easiest thing, but
absolutely.
I imagine is there materials that they can refer to when they go through those
yes,
steps?
there's a process for trimming that we follow and we can share.
Okay, great.
Yeah.
Another one from the Q&A is, can the cameras be reverse mounted to monitor other towed systems, for example, nets?
Interesting. Yes, I think so. We do custom development and slight tweaks and modifications to our products. This system's been designed to operate in a certain way. But as always, we're open to conversations and understanding the problem you're trying to solve. And it may be that you don't need this system specifically, but you need parts of it. And we're definitely open to having that conversation.
How to use the towed, how to use the towed camera as an alternative to observation class ROVs when video is required along a cable route?
So the big difference between like an OBS class ROV and this system is it's been designed to tow straight or curved transects and repeated footage, repeated stills or video at a very kind of consistent speed and altitude. Different with an ROV, my experience, you wouldn't always, it wouldn't be a common practice to fly the ROV and have the ROV pilot going forward while the vessel is also going forward and trying to maintain like a lockstep velocity ahead. This system's been designed to cover like kilometers, and ROVs are usually for like covering a specific area in high detail. So kind of two different applications. One's better for one thing and one's better for the other. I think I answered that. I'm not quite sure.
And another question from the Q&A, how much is the cost of a 380 meter system roughly?
We can chat more about that. It depends on if you need like a winch. It depends on how much infrastructure you have in place with your vessel. So, but it ranges from, it can be anywhere from 40K up to 100 at the higher end when you need everything. If you're missing all of the equipment to get started and you need a boom, to an A-frame kind of thing, a winch, all of the cabling, everything, you'd be on the higher end of the spectrum there with costs.
And what's next in terms of product development for subsea imaging?
So the tow camera system is released. It's going live tomorrow, I believe. New website and all of that. And we're putting some final touches here in production. We're waiting on some longer lead time parts and to build up stock. So we've got some stock now, and we're building up some more. Then we're going to be looking into autonomous battery systems, I believe, next. We'll see.
So the next question is really a little bit interesting. I'm not sure how to interpret it, but it says, why Newfoundland?
Why Newfoundland? Yeah. So,
Yeah.
well, here we're on the East Coast, out in the middle of the Atlantic, and it's cold and a bit harsh, but we like it. That's where we're from. And it gives us a good area, a good hazardous environment to test rugged equipment. So that's the outside kind of view. From the inside, we just like it here. There's a lot of outdoors and a lot of good outdoor activity, skiing, hiking, and all that kind of thing.
So that's all the questions we had from the RSVP, and I don't see any others on the Q&A. And I don't see any hands raised. So with that, I'd like to thank you, Chad, and for your great presentation with subsea imaging. And for everyone else that's here today, if you've missed any of our past presentations, you can find them on the Scripps Oceanography YouTube channel. There's a specific channel for the Scripps Technical Forum. And as always, thanks for attending, and thank you, Chad.
Thanks, Doug.